For anyone who was not at the meeting yesterday, this is going to be a brief introduction to cover the ideas we talked about yesterday. The main idea being this: vectors. What is a vector and what can we do with them? I want to first of all say every single one of you at some point will have played a game that involves a vector. And this is a little example of how that might have looked, okay? You've got a game, you're throwing a ball on the computer, perhaps it's a basketball loop you're aiming at, and you have to aim using those arrows. I want you to ask yourself, which arrow is more vertical? Which one will throw it in a more vertical direction when you hit enter? And which one will throw the ball with more force? Okay, so we've got two questions there. Which aim or which throw would be more vertical and which one would have more force behind it? And I hope that all of you can intuitively see that the black arrow is pointing towards the sky. It's going to be much more upwards in its throw. Meanwhile, that blue arrow, it's quite an extreme throw. It's going to be nearly double the size of that black arrow. And that means there is more force behind it. These are vectors, okay? And the difference between a vector and what we call a scalar is that it's not just about the strength of that throw, it's also about where it goes, okay? And that idea can be carried across to all vectors. It's not just the measurement of the magnitude of the amount, it is also about where it went. To summarize again, a scalar quantity is defined by size or magnitude. A vector quantity also has direction. Now here is several scalar and vector quantities, and we are just going to organize them out. Now force, we've just said, is a vector quantity. It has a size, it has a direction. Area, good old-fashioned area. When you write your answer to calculating the area of a circle, what do you write? It's centimeters squared, 25 centimeters squared. And then you don't write anything else. Nobody writes area 25 centimeters squared north, okay? That's not how it works. Time, I'll say it's a debatable one only because of time travel, but in general, time is scalar. We talk about 6 minutes. We talk about 30 hours. We're not talking about going forwards and backwards. Now, speed. Speed is something we've come across before, and it goes hand in hand with velocity. So speed is something that we've done in speed distance time, and again, when you think about how you wrote your answers for that, you just wrote 25 miles per hour. On the other hand, if you had velocity, you are going to have 25 meters squared at 34 degrees. Okay, so at the end of that, there will be a sort of direction or a bearing. It could be 25 miles per hour north. And if that whole bit is your data, your information, that's velocity. And it's the same idea with distance. Distance is just 25 kilometers. Displacement is 25 kilometers east. Okay, so they come in pairs, and you're never going to get asked, or it's highly, highly unlikely that you'll get asked, name me 3 vectors, at least not in maths, quite likely in physics. What you will get asked in math is a question where they don't tell you you're working with vectors. And you've got to figure it out from the fact they're saying velocity, they're saying displacement, they're saying force. Okay? Now, big question, how do we write vectors? Because this is how we draw them. We draw them as an arrow. This is another version of that. But that's not going to be very concise. If we try to do problems and we're trying to shorthand, we like to be concise. So what I've shown you here are 3 different ways you can do it. This one, you can't even tell on the computer, is a bold U. And that is what we would do on the computer where we can write in bold. Unless you're going to regularly swap to a felt tip pen, it is very difficult for you to write in bold. So what we do instead is we do a U with an underline, okay? And that's the way most people would write their vectors. This one here is another important way of naming it though. It's AB with a little arrow above. And what this says is we go from A to B in that direction, okay? A to B in that direction. If this arrowhead was pointing the opposite way, that would change how we'd write this vector. It's not going to let me do this, is it? There we go. Okay. How we would write this instead, you may be able to guess, is B to A. So we've started at B and we've ended at A. But going back to the way things were, you may be asked to name these vectors different ways. And I can promise you I've copy and pasted these vectors. So in general, the theory should be there that they're all the same length. These are all the same size of vector, and they also are all parallel to each other. But we have to name these vectors. So it's going to be AB, like before, and we pop a little arrowhead on the top to say we're going from A to B. So, vector U equals A to B. And these are 2 ways we can write vectors. Okay, when you're asked to name a vector 2 ways, these are the 2 ways. We look over here. Now I've just told you that these are parallel and they're the same length. They are the same vector. It doesn't matter where they are on the page. Vectors are irrelevant of where. Okay, so we are still going to have vector U go, is equal to something. Now, what is vector U equal to? It is equal, well, we're starting from C, we're going to D, and it is a vector, so we put our hat on it. Okay? And I could start doing the same thing again. So if I paste this again, I want to call this vector U. It's the same length, it's parallel, but unfortunately it's not the same, okay? And the reason it's not the same, you may have noticed, is that the arrow is pointing the opposite direction. So what we're going to do is this is not vector U anymore. This is negative U, okay? And that negative in front just means it's going the opposite direction. If you reflected it in a mirror, that would be it, okay? And we're naming this vector, so where do we start? We started at we started at F, we went to E, and it is a vector we have, so we put our little vector hat on it. When we name vectors, it doesn't have to be U. It could have been V, it could have been W, it could have been A, it could have been B. It's like algebra though, in that we like them to follow an alphabetical order. So these are our ways of naming vectors, where you're coming from, where you're going to. If they are the same vector, we can call them the same vector. Vector AB equals vector CD equals vector U. If they are identical but going the 180 degrees the opposite way, then it will be negative U. Okay, so this is just a little summary of a couple of other things we can do now. Similarly to it going the opposite way, so similar to the idea of it going the opposite way, that we can just write it in terms of U, so we can write it as negative U, we can do the exact same thing for if you're going the exact same direction but twice as far. So here I have copy and pasted that line, and I can tell you for a fact that 2 of these fit into G to H. So vector AB is U, but 2 of U, is actually equal to GH. Okay, and again, we put that little hat on it to say it's a vector. Okay, so we can write one vector in terms of another vector. Okay, so GH is equal to 2U, AB is equal to 1U. Okay, so that's another little thing we can do. And 8, this is the last thing, and it's actually one of the key ideas. We can add vectors. And here's our formula. AB plus BC equals AC. What you will notice is that it does not matter where B was. What matters is where you start and where you end. And I used an example yesterday of if you started in Glenrothes, flew all the way around the world to New Zealand, then came back to, say, Kirkcaldy, your journey would only be from Glenrothes to Kirkcaldy. It would not matter that in the middle you had been off having a barbecue in New Zealand. Okay? So that is the idea of adding vectors. It doesn't matter where you start, where you end. It doesn't matter where you go in the middle. What matters is where you start and where you end.